Hi, the lecture today is a review on logarithmic functions. We are going to take a look at properties of logarithm and do a quick review of this topic. Let me mention that most functions come in pairs. What do we mean by pairs? Well, we are really talking about a function and its inverse function. We have taken a quick look at inverse functions in the previous lecture, and here I am referring to that. For example, if you have a function which is simply y is equal to x plus 2, the inverse of that, the inverse of this addition is going to be subtraction. X minus 2 is the inverse function of x plus 2. Similarly, if you have a function which is like say 3x, the inverse of that, the inverse of tripling an input is dividing it by 3. That would be the inverse of 3x. If your function is say x cubed, the inverse function of that is cube root of x. These type of pairs of inverse functions are the ones that are most intuitive and accessible right away. Finding inverse function in general could be a lot more complicated than that, and one topic that is at hand right now is the topic of logarithm. Logarithm is really the inverse function of the exponential function. Let me write that down. Logarithm is the inverse function of exponential function. What do we mean by that? Let's go back to a simple exponential statement. Suppose I have the following type of a question. I ask, find the missing number find the missing number in the following equation. 2 has to be raised to what exponent? Adjust my pen. 2 raised has to be raised to what exponent to give us say 8. Well, you know the answer from memory. You try various exponents of 2 until one matches this friendly problem. 2 to the power of 1 is 1, 2 to the power of 2 is 2, 2 to the power of 3 is 8. So here you say the answer is 8. Excuse me, answer is 3. Now suppose I want to abbreviate all of this question in a notation. The notation that we are going to use is going to be a new name. It's going to be logarithm of. We're going to write this number 8 up here. This base 2 is going to be written down here, and the answer that we found is going to be written here. So the notation of this logarithm that is used in conjunction with the exponential notation we had before is going to be like this. Logarithm of a number in a base is a number such that if this base is raised to that exponent, we get our original number back. So when we say, for example, b to power of say x is equal to y, another way of writing the same thing is to say x is equal to logarithm of y in base b. These are stating the same fact. Let's just review what we just said. We said if you write 2 to the power of 3 is equal to 8, that is expressing the same information as if you were saying that 3 is equal to logarithm of 8 in base 2. Let's go ahead and do some basic exercises on this topic. What is logarithm of 100 in base 10? Remember, this is restating the following question. Find the missing number in this equation. 10, that base, has to be raised to what exponent to produce 100 for us? Well, from memory we know that the answer is 2. 10 squared is going to be 100. So logarithm of 100 in base 10 is 2. Similarly, logarithm of 1000 in base 10, what is that number? That answer is just 3, because 10 cubed is going to make 1000 for me. Let's try another one. What's the logarithm of 0.25 in base 5? Excuse me. What's the logarithm of 0.25 in base 2? That's a little bit more complicated. Well, first let's write this thing in a fractional notation. 0.25, same as a quarter, 1/4. What's the logarithm of that in base 2? Again, a rather unfamiliar situation. We go back to a more familiar notation, which is what we are trying to find is an exponent, a missing exponent, that if 2 is raised to that is going to produce this number for me. Well, how can I make a fraction? Obviously my exponent had to be negative, and then how can I make 4 out of raising 2 to some exponent? I needed to square 2. So I have to do two things. One is to make the exponent negative and also produce a 4 out of it. So I will get the answer of -2. 2 raised to the power of -2 is going to be 1/4. Now I give you a question here and you try to do that. What is logarithm of 0.125 in same base 2? Follow the same strategy here. First, convert your number to a decimal. Excuse me, convert your number from decimal to a fraction, and then come up with the answer. Perhaps if you need to use that, then you can use that notation. So you can pause the video for a while, answer that, and come back. Continue. 0.125, if you're not familiar with it, you can, if you don't know the fraction that is equal to it, you can write it like this. 0.125 is same as 125 over 1000. Now you can start to simplify this thing for yourself. Divide by 5. Obviously both of these can be divided by 5. That makes 25 over 200. Again, both of these are divisible by 5. That makes 5 over 40. And that can be done again. You can divide by 5 one more round. This is 1/8. So it's good to know that 0.125 is same as 1/8. Question 2 should be raised to what exponent to create 1/8 for me? And the answer is obviously -3. You need negative to make the number go into the denominator, and you need a 3 to create 8. Okay. Now what we want to do next is derive or explain rules of logarithm. So rules of logarithm. Well, in a previous lecture we talked about rules of exponents. So we learned rules of exponents such as if you have 2 cubed times 2 to the power of 5, same bases, some exponents, you can go ahead and add those two exponents. We just mentioned that exponential and logarithm are two closely tied functions. One is the inverse function of the other one. So we would expect that whatever rules we had for exponents are going to show themselves when we are studying rules of logarithm. In fact, the rules are the same. They're just expressed in different format. It's easy enough to list the rules and try to memorize them and such, but I'll try to go ahead and explain where the rules come from, so that in case you are confused while solving a problem, you can go back and retrace the logic behind the rules and perhaps choose the correct formulation. To explain the rules, first rule that I want to explain is the following. The rule says if you have logarithm of a number times another number, so two numbers are multiplied, what you can do is to take a logarithm of one of them, take the logarithm of the other one, and then add them to each other. It does not matter what base you have here. The base could be any number you wish, so long as all the same number. So for example, logarithm of that in base 2 is equal to logarithm of a in base 2 plus logarithm of b in base 2. Same thing would be valid if you were doing it in base 3 or 5 or any number. Just to avoid having an alphabet soup of too many things floating around, I just wrote 2 here. Let me go ahead and justify this rule for you. Then I come back and explain what is the significance of this rule. What is so big deal about it? In fact, it started something similar to a revolution in the scientific community when that simple formula came out and when logarithms were introduced. They were, in a sense, the computers of their own time a few centuries ago. Okay. Suppose the number a that I'm using here is itself 2 raised to some other number. Let's call it x. Like for example, if a is 8, x will be 3. If a was 16, x will be 4. A was 32, x will be 5. And so on for all sorts of other numbers. And similarly, suppose that this number b that I'm going to talk about here is itself 2 raised to some other number, say y, just like that. What did we mention right now? If I have a is equal to 2 to the power of x, another way of saying the same fact, writing it in our notation, is to say that exponent is a logarithm of that number in base 2. That is, x is same as logarithm of a in base 2. Is that right? Let's just go through an exercise one more time. If a was 8, logarithm of 8 in base 2 would have been this 3. If a was 32, logarithm of 32 in base 2 would have been 5, and so on. Whatever this number is, it's going to show itself as a logarithm as well. Similarly, another way of writing this is to write y is equal to the logarithm of b in base 2. Now, we are talking about multiplying a and b, so let me go ahead and just multiply a and b. A times b, now I have to multiply 2 to the x times 2 to the y. Well, in the previous lecture we learned about rules of exponent. x2s and y2s, you multiply them, you will have x plus y2s, 2 to the power of x plus y. Okay, so a times b is 2 to the power of x plus y. Now with the notation we learned, if I were to ask you what is the logarithm of a times b in base 2, what would you say? Logarithm of a times b in base 2 is the exponent that if 2 is raised to that, we produce a times b. Well, the exponent we need to raise 2 by is x plus y. All right, logarithm of a times b in base 2 is x plus y. But who was x? X, here's the x. X itself was logarithm of a in base 2. So let me write that. Logarithm of a in base 2. That is x. How about y? Here's y. Y itself was logarithm of b in base 2. And then you're adding these. We are saying that is equal to the logarithm of a times b in base 2. Okay, the rule of logarithm we just were promising here, the logarithm of a product is equal to the sum of the logarithm of the pieces that are involved. And here we gave a justification for that formula. Let me try to drive this point home by giving an example. Suppose a is 8 and b is say 16. What is logarithm of 8 in base 2? That we know is 3. How about logarithm of 16 in base 2? We know that is 7. What is a times b? A times b, 8 times 16. You multiply them, you get 128. Do we know what's the logarithm of 128 in base 2? Logarithm of product in base 2. How many times should I multiply 2 by itself to make 128? Let's try it. So far I got 4. Now 8. Now 16. Now 32. 64. Now 128. So this was 4, 8, 16, 32, 64, made to 128. How many 2's did it take? 1, 2, 3, 4, 5, 6, 7. I realize my mistake now. Let me go correct. I said something, I wrote something else. Sorry for that. I hope I didn't confuse you. So now, what is it that we have? Let me go back here. Logarithm of 8 in base 2 was 3. Logarithm of 16 in base 2 was 4. Logarithm of 128 in base 2 is 7. What does 7 have to do with 3 and 4? Well, let's just sum up those two. So logarithm of 128. 128 itself was 8 times 16. This 3 was a logarithm of 8 in base 2. 4 was logarithm of 16 in base 2. You add them and you get the same answer as you have on the other side. Okay, apart from some rule in mathematics, what significance does this thing have? Why so much emphasis on logarithm and this rule? Well, in the days before computers, people had to do all sorts of computations by hand. So scientists had to spend days after days of multiplying and dividing and things like that. And it could easily consume half a day of a scientist just to do basic arithmetic. Logarithm simplifies that arithmetic tremendously by essentially outsourcing the job. How does it do it? Well, if you look at on the left hand side of this rule, you see that you have a multiplication to carry out. This is what you want to avoid. Now, most of you are from the calculator generation. You don't even remember anything before calculators and computers. So it's rather unlikely that you have multiplied long numbers, like 2 5-digit numbers. Probably haven't sat down and multiplied 2 of these things to see how painful that is and how long it takes. but that's what people had to do all the time. So if you have to multiply numbers, so can I simplify that task? What logarithm does is that it simplifies multiplication to level of addition. Instead of multiplying two numbers, all you have to do is to add two numbers. Addition of numbers is a lot less painful than multiplication is, and that is the secret to success of logarithm. But of course nothing comes for free, and the catch is that somebody had to calculate the logarithms. So you could hire someone to calculate logarithms of lots of numbers, and that's going to produce so-called tables of logarithms that used to show up at the end of your textbooks, and the scientists would use those tables to calculate their numbers. Later on they invented slide rules, and they would do those calculations even faster. But nowadays, if you want to multiply numbers, you simply use your calculator and you bypass a lot of these things. But logarithm has many other uses in mathematics, and so we are going through these properties because we do expect to use them later on. Let me quickly go over some other rules of logarithms. So here we had rule number 1. Logarithm of a product is a sum of two logs. Rule number 2. Logarithm of a ratio is a difference of logarithm of the numerator and denominator. Again, it doesn't matter what base you have. Still true if you could have base 3 or 4 or any common number as a base. How does this one get to be established? Again, let me quickly demonstrate this thing for you. Suppose a is 2 to the x, which is same as saying x is a logarithm of a. Suppose b is 2 to the y, which is same as saying y is logarithm of b. What is a over b? A over b is a ratio of these two. Now you see the rule of exponents says subtract the two exponents that you have. Well, what's the equivalent form of saying this? The equivalent form of saying this is to say that the logarithm of a over b is that exponent. Logarithm of a over b is just x minus y. But x is just logarithm of a over 2. Y is just a logarithm of b, b in base 2. And the difference of these two is a logarithm of a logarithm of a over b in base 2. So that is the second rule of logarithm. Logarithm of a ratio is difference of a logarithm of numerator and denominator. Property 3 that we have is that logarithm of a number raised to some exponent. Let me just use a exponent, say n in base 2, is same as that exponent times the logarithm of that number in base 2. Again, instead of 2 you could have had any number you wished. Let's demonstrate this for a particular exponent so that we don't have too many variables in our presence. Suppose I want to show that logarithm of a to the power of 5 in base 2 is same as 5 times logarithm of a in base 2. So what happened is that this exponent has come in front of the logarithm. How does that come about? As usual, let's start by saying, suppose I know that a is some power of 2, which is same as saying x is a logarithm of a in base 2. These are same statements. What do I want to study here? I want to study a to power of 5. Well, a to power of 5 means 2 to power of x, the whole thing raised to power of 5. As usual, rules of exponents are basis of all of our conversation here. Well, what is the simplified form of 2 to the power of x to the power of 5? We learned in exponents that you multiply these to old and new exponent. Well, what does that say? It says that if I want to take the logarithm of this expression, if I want to take a logarithm of a to the power of 5 in base 2, logarithm of a to the power of 5 in base 2, I would get whatever shows up here. Logarithm of that in this base would be the exponent. So I just write the exponent here, 5x. Now I go ahead and say I already knew what x is. X was that, logarithm of a in base 2. So all I'm doing now is I'm multiplying it by 5. So what I have is that 5 times, instead of x, I have logarithm of a in base 2. This x is just that. That is same as logarithm of a to the power of 5 in base 2. So that's the demonstration of this rule that we had in mind here. Let me just give you a particular exercise to do. Suppose I want to find logarithm of 4 in base to the power of 5 in base 2. You can take 4 and raise it to the power of 5 if you wish. It's going to be a large number. Perhaps you might not be comfortable with that. It's 1024, and take the problem from there and solve it. But it's a lot easier if you realize that this 5 can be moved in front. Now logarithm of 4 in base 2, that's easy enough number. That's just 2. And the final answer becomes 10. Okay, so that was another rule of logarithm. Let me mention some other basic rules. What's a logarithm of a number in base itself? So answer this like this. B raised to what exponent will be b? Obviously the answer is just 1. Let's look at some other special case. Suppose I have question, logarithm of b raised to power of 2 in base b is going to be what? So we are asking b raised to what exponent will be b to the power of 2? Well, the answer is just what we said, is just 2. And so on. If I had logarithm of b cubed in base b, I'll be looking for a number such that if b is raised to that, I'll get b cubed. Obvious answer is just 3. So all of these can be summarized in one rule. Logarithm of b to the power of n in base b is just n. This is one of the formulas that shows the interplay between exponents and logarithm, that they are inverse functions of each other. B to the power of n, that's the exponentiation. You take a logarithm, you come back to the exponents you had started with. Now to the other side of the coin, suppose I ask you what is 2 raised to the power of logarithm of 8 in base 2. Well, You can have two ways of doing this. One is just doing it by brute force and going through the motion. That is, you might go ahead and find out what's the logarithm of 18 base 2. That is 3. Is that right? And then say, what is 2 raised to the power of 3? Well, the answer is obviously 8. Now, is it a coincidence that this number is same as that number? No, it's not a coincidence. If this base of the exponentiation and the base of logarithm are the same, then the two actions you are going through are going to cancel each other out, and you are going to end up with the number that you were using the first time around. Let's try this thing one more round. Suppose I say, what is 5 raised to the power of logarithm of 25 in base 5? Well, logarithm of 25 in base 5 is a number that if 5 is raised to that, you are going to get 25. And that's exactly what you're doing here. You're taking 5 and raising it to all of that. So here you have 5, and that is just 2. And it's no surprise that your final answer comes out to be just a number you had started with. So is that coincidence? Again, no, it's not a coincidence. That always happens. If this base and that base are the same, the two activities are going to cancel each other out, and you end up with the number you had started with. So even if the numbers we are dealing with are not such a friendly numbers, the answer will be obtained in the same way. Suppose I wanted to ask you, what is 3 raised to the power of logarithm of 7 in base 3? Now in this case, we don't have the luxury of being able to calculate this thing easily. What's a logarithm of 7 in base 3? It is some number, but not a friendly number. But that's not necessary. Whatever this number is the number that if 3 is raised to that exponent, that number has the property that if 3 is raised to that exponent, we are going to get 7. That's the meaning of this logarithm. And here we are saying take 3 and raise it to that exponent. Take 3 and raise it to that exponent. Whatever that exponent is, that mystery number, not so important for us, because we know we are going to get 7 at the end. So in general, we have the following. B raised to the power of logarithm of any number in base B, so long as these two numbers are the same, is the number you have started with here. That's A. So that's another fact that shows the interplay between logarithm and exponential. One of the things that justifies why we are saying these two actions are inverse functions of each other. There are still other rules of logarithm, such as a change of base rule and other properties of logarithm. We are going to study them in much more detail later on when we learn about differentiation and other things in calculus. So right now we're just reviewing properties of logarithm. Okay, let's go ahead and recap the rules that we have learned so far. These are the main rules. We have logarithm of a product in any base is equal to sum of the logarithm of the individual pieces of the product in that same base. Logarithm of a ratio in a base is equal to the logarithm of numerator minus logarithm of denominator. Logarithm of a power is equal to the exponent times the logarithm of this number used as a base here in the original base of the logarithm. we have logarithm of b to power of n in base b, that is just n. Special case of this is the logarithm of 1 in base b. What's the exponent of b? B raised to what exponent will be 1? Obviously the answer is 0. B to power of 0. If this is 0, this answer is also 0. The other side of the coin was that b raised to the power of logarithm of, say, a in base b is just a itself. There is still one more rule, change of base formula. Let me motivate that by going through a short discussion. So let me make space here for change of base formula. Maybe I write it now and then come back and point it out again. Logarithm of a number in some base b. If for some reason you didn't like this base and you want to change it, you have the following option. You can take the logarithm of a in some other base, say c, and divide that by the logarithm of this base in the new base c, and then you will get the same answer. Where does that formula come from? Let me go ahead and justify the whole thing by talking about special bases. So in this formula, logarithm of a in base b, what kind of bases would be good to use? Well, it depends on the problem, but customarily there are some numbers that are used more often than others. One of these numbers is just 10. So base 10 is important because we do all of our numbers in base 10. So logarithm in base 10 is one special logarithm. On your calculator, this is probably shown by a capital L or G, or perhaps all capital. So this notation of L or G in capital is used on calculators and in some text. To indicate that you are doing base 10 calculations. Let me just point out what's the significance of base 10 calculation. Suppose I ask you what's the logarithm of 100 in base 10. 10 squared will be 100. Logarithm of 1000 in base 10. So that's going to be 3, and so on. So what's the number that comes out? That number is just a number of zeros that you have here. Another base that is significant is base 2. So logarithm of a number in base 2. This gets to be used very often in computer science because of the binary nature of computers. That kind of a function comes in. Most calculators don't have a special button for this. The other base that is important is base e. We talked about e in a prior lecture. It's a special number just like pi. Its approximate value is 2.71828, etc. Logarithm of number, when it's taken to this unusual base, turns out to be easiest type of logarithm to deal with, and for that reason it is referred to as a natural logarithm and has a special notation for itself. They use ln to indicate natural logarithm. So On your calculator also this button definitely does exist. This is a universally accepted notation in addition to the basic notation of a logarithm itself. These two are universal. That other notation with a capital, some people use it to mean other things. So do make sure that you locate these two buttons on your calculator and learn how to use it on the calculator. Now comes up the question, suppose for some reason in a problem you were interested in finding logarithm of 7 in base 3. How would you find that out? So we don't know what the logarithm of 7 in base 3 is. Let's just for the moment indicate it as x. We want to try to find out what that x is. Let's go ahead and rewrite this thing in a different way that's going to justify for us this formula I mentioned here, the change of base formula. So again, the point is that your calculator doesn't have a logarithm base 3 button on it. What if you wanted to calculate this? Could you calculate it using the other buttons that you had? Well, it takes a little bit more work to learn how to use those other buttons. Let's go ahead and write this in the exponent notation. Whatever this number is, whatever x is, has the property that if 3 is raised to that power, so 3 raised to power of x is supposed to be 7. This is a exponential format of the same fact. Now I say let's go ahead take logarithm from both sides. Now I say take logarithm from both sides. If you want to take a logarithm, you have to decide what base you want to use. But that's up to you. If you want to use base 10, base e, or whatever base that is comfortable to you. Let's use base 10. Say in base 10. So I will be using logarithm base 10 of left hand side, and that's going to be equal to the logarithm base 10 of right hand side. Now we go ahead and use the following rule of exponent we learned here, that an exponent goes in front of the logarithm. So come back here and say this exponent can go in front, and the formula is going to look as x logarithm of 3 in base 10. That is equal to logarithm of 7 in base 10. Now logarithm of 3 in base 10, your calculator has a button you can use to calculate that. In this one, same way. You take the right hand side and divide by this coefficient to get your x. So x becomes that quantity, logarithm of 7 in base 10, divided by this quantity, logarithm of 3 in base 10. Okay, so remember what was it that we were after? We were trying to find out. Question was, what is a logarithm of 7 in base 3? That's what our x was. That's a logarithm of 7 in base 3. So I went and chose some other base, didn't matter really, 10, to take a logarithm of both of these numbers in that base and divide them with each other to get the value of this logarithm. So here we have change of base formula and justification for it, and that was the last formula we had in this sequence of formulas here. Let me make sure I separate these two, because the writing kind of gets out of hand and formulas tend to run into each other. Make sure you see where everything is. So like this is the base of the logarithm, this is a base of an exponentiation, this is a base of an exponentiation, its exponent is all of this, and so on. Here's a fraction, numerator, and here's a denominator, and so on. So you need to practice these formulas and solve several problems. Okay, next topic we are going to talk about related to logarithms is the graph of logarithmic functions. First, let me quickly remind you of an exponential function and what its graph look like. We have practiced with dealing with functions such as 2 to the power of x, and we know the graph of that looks something like, suppose this is 1, so at 1 we have 2, and at 2 we have 4, minus 1.5, and so on. And we have a graph kind of looking like this. Graph of y is equal to 2 to the power of x. What's the inverse function of this? Inverse function of this is a logarithm of x in base 2. Not all that familiar with that, we might as well start with a table. On our table we go ahead and pick some friendly numbers we can easily handle. What are the numbers for which we can calculate logarithm in base 2 without using a calculator? Well, logarithm of 2 in base 2 is 1. Logarithm of 4 in base 2 is 2. Logarithm of 8 in base 2 is 3. Logarithm of 16 in base 2 is 4. So on. So every time we double here, we are adding 1 to this one. Let's back up. What's the logarithm of 1 in base 2? We learned in properties of logarithm. That's a 0. How about half? What is logarithm of 1/2 in base 2? Answer is it's minus 1, because 2 raised to the power of minus 1 is a half. Logarithm of quarter in base 2, minus 2. Eighth in base 2, minus 3, and so on. So on this side we see that we are quickly approaching infinity, and this one also approaches infinity but a lot slower. On this side we are approaching what number is it? As I go to the left, I am approaching 0, of course. Where do these numbers go? These numbers are going to tend toward minus infinity. Let's go ahead and graph these numbers that we have here. Let me choose this as 1 and 2, 3, 4, 5, 6, 7, and 8, 9, 10, 11, 12, 13, 14, 15, and 16. We know at 1 logarithm was 0, at 2 it was 1, at 4 it was 2, at 8 it was 3, at 16 it was 4. At half, here's a half. At half it was supposed to be minus 1, so is it almost minus 1. A quarter, so that's minus 2. An eighth, minus 3, and so on. So the picture that the curve that connects all of these points is going to look something like this. So this is a graph of y is equal to logarithm of x in base 2. Now we did this thing from scratch, but we could have paid attention to the following, that if I were to graph y is equal to 2 to the power of x, the graph we just mentioned here, I'll be using using the same table, except that for this one these guys are going to play the role of x, and these guys are going to play the role of y. So for example, 2 cubed will be 8, 2 to the power of 4 is going to be 16, 2 to the power of minus 3 is going to be an 8. There's one more reason why these two functions are called inverse functions. So if this is x, that's going to be y, opposite of what we had here. So if I were to graph that alongside with the graph I just drew, I will discover something we have seen on the section on inverse functions. For example, at minus 3, here is, let me go ahead, mark my axis here. Here's minus 1, minus 2, minus 3. Here's my vertical axis. Of course, this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on we go to the power of minus 1. That was a half. To the power of 0 is 1. To the power of 1 is 2. To the power of 3 is 8. Let me make sure I made this right. 2 to the power of 1 is 2. 2 to the power of 2 is 4. To the power of 3 is 8. And I don't have much room to go, or maybe I have to borrow a little bit of space here. 9, 10, 11, 12, 13, 14, 15, and 16 will be here. So the other point will be all the way at this location. Let me see if I can connect these points. So this is a graph of y is equal to 2 to the power of x. And this is a graph of logarithm of x in base 2. One big lesson about inverse function is a peculiar symmetry property they have. How should I reflect this graph to get this one? Or how should I reflect the graph of logarithm to get the graph of exponential? Any pair of inverse function have the following property, that if you take graph of one of them and reflect it across the 45-degree line, my picture is not nicely drawn to scale, but if you draw the 45-degree line, y equal to x, or the so-called 45-degree line. If this was a fold on a page, dotted line on a page, and you are folding the page across that, the graph of this function will coincide with a graph of its inverse function. So this and that will be reflections of each other in this mirror. The mirror is sitting at the 45-degree line, and reflection of one of them will be the other one. So in graphing a logarithmic function, one way you can go about it is making a table and practice that and just get it down like that. The other way you could do it is to remember the original exponential function and reflect it across the 45-degree line. You will get the graph of your logarithmic function. Some of the questions in this section bring in issues you have learned from the section on shifting and scaling and such. So here's a question: graph y is equal to logarithm of x minus 3 in base 2. What we want to know is what's the influence of this minus 3 on the picture. So how do we go about the discussion here? Graph of logarithm of x in base 2, we have learned how that one looks like. Here are the essential points. It crosses the x-axis at 1. It has a vertical asymptote at y-axis itself, and it looks more or less like this. This is a graph of logarithm of x in base 2. If you want some special points on it, just go after the friendly numbers and you'll have specific numbers to work with. Now, adding minus 3 to x, what is the influence of that on your picture? One discussion we had in the section 1.3 was that if you replace x minus 3, that's going to shift the picture by 3 units to the right. So if you take x and replace it by x minus 3, the net effect on the picture is that it's going to shift to right by 3 units. Somewhat puzzling to students that we are actually going to move right. So if you go 3 units to the right, how can we show that clearly? Let's take a look at important points. Like at this point 1 is going to go to 1, 2, 3, and 4. That's the new location of the x-intercept. This vertical asymptote that was at 0 is going to move to the right also. That's going to be at 3. So this is the new asymptote, x equal to 3. Here is the graph of this function. This is y is equal to logarithm of x minus 3 in base 2. One way to check your answers, make sure that you are shifting in the correct direction, is by checking certain numbers. For example, if I put 4 here, 4 minus 3 is 1, a logarithm of 1 is 0. So I'm correct in thinking that 4 is the new x-intercept. So you go ahead and practice other questions from this section on the logarithms, and we'll be ready for calculus in the next section. Good luck and God bless.